Welcome back to ECE 442-542. In this video, we're actually continuing with numerical integration strategies for performing discrete equivalence. In this one, we are actually using the backward rule. Remember, we were trying to find the little sliver of area that we were now adding on to when we were doing the integration. Now we are saying let's look backward in time from the present time, and we now want to take this little area or use the backward integration strategy, and in fact this video is looking at solving problem number 5 in homework number 4. We're doing scenario number 1 where we're trying to do a direct input-output discrete equivalent. We're not incorporating any dynamics before or after the transfer function capital H of S. We're going from the input E to the output U. We want to now find what is our state space representation that would represent capital H of S to capital H of Z. We derive these different expressions or substitutions, or what's the operation in the Z domain, consistent with the operation of S in the Laplace setting. This particular video is working with the backward numerical integration strategy, so that's now this quantity Z minus 1 over capital TZ. Again, for the setup, we have our different state space matrices. We have A, B, C, and D for the continuous time. We want to now find what is phi, gamma, H, and J using the backward numerical integration discrete equivalent strategy. And in this particular case, this vector, state vector, in the discrete time setting is not going to be a sampled version of the state vector little x of t in the continuous time setting. It'll be related, but it won't be a direct sampled version of little x of t. Let's now find what these expressions for phi, gamma, H, and J are when we want to use the backward numerical integration strategy. We begin exactly the same way. We simply Laplace transform the state space representation of the continuous time system, and the only operator S that exists in that representation is the S on the left-hand side of the equality in the dynamic equation, where, remember, when you differentiate in the time domain, that's equivalent to multiplication by S in the frequency domain. We want to use the backward rule, which means that we replace S with the appropriate Z expression, and in this case the Z expression is now going to be Z minus 1 over TZ. That's now going to be substituted in for S, and the only place that that gets substituted is right there. The arguments again are just saying, oh, we're in the Laplace setting or we are in the Z setting after the substitution in the discrete time case. Doing that now says that we replace S with Z minus 1 over TZ. That now scales capital X of Z. That's equal to A X of Z plus B E of Z. We can eliminate this ratio of Z terms or expressions by multiplying both sides by the sample period capital T times Z, and that gives us then Z minus 1 scaling X of Z is equal to A tz x of z plus btz e of z. And now, as you will see, we now actually have this z operation applied to multiple vectors in this expression. In the forward strategy, it just appeared on one term. Now it's appearing multiple places. Let's now collect all of those terms that are a power of z of 1, scaling capital X of z, and then the constant factors of x of z, and then we also have, just remember, this btz scaling e of z. Or what I'm trying to say is, let's now on the left hand side write down all of the terms that are scaled by z. So we now have z x of z, that's this one. Then we have minus atz x of z, that's this one. But we can clean that up a little bit. Do you see that we can actually factor out a common z x of z from both of those terms? And in order to combine a matrix A with a scalar t product with this scalar, we need to introduce the identity matrix I. Or rewriting that and factoring out the common z capital X of z factor, we now have I minus a t z capital X of z equaling, do we have anything? Well, we have to remember we still have this term on the left hand side. So now we have 1 times x of z, that's this term, and since it was a minus on the left hand side, if we add capital X of z to both sides, it comes over with a plus 1 x of z, and we could write that as an identity. We could write it as really just a scaling of 1, so I'm just going to leave the scaling off, plus btz e of z. That's now our expression in the frequency domain that we need to convert into the time domain. If we now go into the time domain, what happens here? Do you see, in fact, that we now, and if we break this apart, we have I z x of z, and we have a minus a t z x of z. What are those going to look like in the time domain? Well, z, scaling capital X in the frequency domain, just advances little x by 1 in the time domain, so that this first term right here drops down to x of n plus 1. This term, together with this z operator, gives rise to minus at times x of n plus 1. And let's go ahead and bring this onto the left-hand side, since it's going to be advanced by 1, and we can call that minus, or that becomes minus bt e of n plus 1. All of that is equal to this. That's the only term that's left, and inverse z transforming capital X of z just leaves us with x of n. This looks a little bit messy. We can clean it up, and a easy way to clean that up is to actually just say, you know what, that's a mess. Let's just define it to be a new vector, and the vector that we are going to use is now w of n plus 1. What have we just said? Well, now we have said that w of n plus 1 is equal to x of n. We just made that, so this is coming from there, and the w of n plus 1 is all of that mess that we just collected into. We made those three terms, formed a new vector w at time n plus 1. And this we are going to use later. This relationship that the vector x in the discrete time setting, x at time n, is actually just w of n plus 1, this new combination of x and e. And we'll call that star when we use it later. What have we done? Well, we actually defined w of n plus 1 equal to x of n plus 1 minus atx of n plus 1 minus bte of n plus 1. Or that's now I minus at x of n plus 1 minus bte of n plus 1. And that's w of n plus 1. That's now the relationship between this new definition we just defined, and that's okay. We can just create a new vector. This new vector w at n plus 1 is a matrix I minus at times x of n plus 1 minus bt times the input at time n plus 1. Well, if that's the case, or the relationship between w, x, and e at n plus 1, do you see that it also needs to be the same at the present time n? Or we now have w of n is I minus at x of n minus bt e of n. And in fact, that's just an equation containing these three vectors, w of n, x of n, and e of n. And they're all at the present time n, which really allows us to say, oh, if we can now solve this equation for x of n in terms of w of n and e of n, we can now use that up here to obtain w of n plus 1 in terms of w of n and e of n. Or suppose we now solve this for x of n. X of n is now equal to, let's multiply everything on the left by the inverse of the matrix that's scaling x of n. Or x of n is now I minus at inverse w of n. And let's put the e of n on the other side, so we're adding plus I minus at inverse bt e of n. That's little x of n. Well, we can use that x of n to get rid of that x of n, so that we now have an equation that uses w of n at the present time and e of n at the present time, and express that combination generates a w of n plus 1. it's now time for this later. Meaning, we now have W of n plus 1 is equal to, well, let me just go ahead and say, here is our later time, where we're now using equation star, which was W of n plus 1 is equal to x of n. And we're now going to use this expression for x of n, so that now we have a dynamical relationship or a dynamic equation in a state vector W and the input E. Or W of n plus 1 is now equal to little x of n, but little x of n is I minus AT inverse W of n plus I minus AT inverse BT E of n. And that's actually what we were looking for. Now our state vector in the discrete equivalent is this W of n, and if that's the case, then this matrix must be our system matrix phi. And this matrix, which now is the input matrix connecting the input E to the state vector W, this is now our gamma. And what is the output equation? The output equation, U of n, is C x of n plus D E of n. But we need it in terms of W of n. And that means that we can use this x of n to get rid of x in this equation for U. Or we can now write down that U of n is equal to C times that x of n expression, which is I minus AT inverse W of n, plus I minus AT inverse BT E of n, plus D E of n. And hopefully you can now see that this becomes C I minus AT inverse W of n plus a more involved direct feed-through term, C I minus AT inverse BT plus D E of n. That's now the output equation, so that this would become our H matrix, and this would become our J matrix, the direct feed-through matrix. And if we needed it, if somebody said, well, what is x at the present time n? We know that x of n is just W of n plus 1, and we have an equation for that. That's what we're keeping track of. That's our state vector in this discrete time representation. With that said, we now have derived the forward and the backward strategies to finding the system matrix phi, the input matrix gamma, the output matrix H, and the direct feed-through matrix J in terms of the state space representation A, B, C, and D in the continuous time setting. We've now derived the second column and the third column, and it can be shown that the last column is the trapezoidal structure, which obviously is a little bit more involved with respect to the combinations of A, B, C, D, and T to produce phi, gamma, H, and J. But these now provide you with a matrix expression in terms of A, B, C, D, and T to immediately compute phi, gamma, h, and j in your discrete equivalent for the three different numerical integration strategies of forward, backward, and trapezoidal.